Good morning, guys. Today we're going to start our unit on random variables. We're going to start that by discussing what is a random variable and then distinguishing between discrete and continuous random variables and how we work with them and find things like expected values and standard deviations. So let's just start with trying to create a sample space of a random event. So consider rolling two four-sided dice with four faces showing 1, 2, 3, 4. What's the sample space for one roll of the two dice? So what are the possible outcomes, that's all sample space means, for what we could get from those two dice. So just kind of listing them out. First dice can be a 1, a 2, a 3, or a 4. But then the second dice can then take on, the same options, 1, 2, 3, or 4. So if we're listing them out, I got 1, 1, 1, 2, 1, 3, 1, 4. I could have 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4. And then same thing with the 4s, 4, 1, 4, 2, 4, 3, and 4, 4. So we get 16 possible outcomes. What we're really interested in is the second part. What's the sample space for their sum? What are the possible sums that I could get? So if we're going through and looking, the smallest I can have is 2. 1 plus 1 is 2. And then the largest I could possibly have would be the 4 plus 4. That would be 8. And I should be able to hit everything in between because there's a 3. Here's a 4. Here's a 5. We've got a 6, and then we've got a 7. So those are all of our possible outcomes for the sum, every number from 2 to 8. All right, so let's look at the probability distribution of that. Now, what is a probability distribution? Just like regular distributions, a distribution is a list of your values and how often each one occurs. Probability distribution is the same thing. It's a list of outcomes from a chance process and their respective probability. What's the probability of each of those outcomes? And their respective probabilities. So, a couple things we need to know. Since it's all possible outcomes from a chance process, your probability distribution should add up to 1. Okay. All right, so let's let X represent the sums. So they could have been 2, 3, 4, 5, 6, 7, or 8. And then what's the probability of each? Well, if we go through, 2 occurred only once. It was the 1 plus 1. So 1 out of the 16. 3, we had 2, 1, and 1, 2. So that's 2 out of the possible 16. 4, we got a few different ways. 1, 3, 3, 1, 2, 2. 3 out of the 16. So if we go through and just finish out the sample space, 5 was 2, 3, 3, 2, 4, 1, 1, 4. It's 4 out of the 16. 6 was 4, 2, 2, 4, 3, 3. So it's 3 out of the 16. 7 was 4, 3, and 3, 4. 2 out of the 16. And then 8 was just 4 plus 4, 1 out of the 16. So this is writing out the distribution. Well, just like any other quantitative distribution, we can write it as we draw that as a histogram. Or we could do it, dot plot or box plot, whatever, but histogram, we typically like to look at these things. So x-axis are the sums, 2, 3, 4, 5, 6, 7, and 8. Y-axis are the probabilities. So 1/16, 2/16, 3/16, and 4/16. We call that 1/4 or 1/8 if you wanted to. So how often did each one occur? Well, 2 occurred 1 out of the 16. 3 occurred 2 out of the 16. 4 was 3 out of the 16. So we would just go through, just like we've been doing, graphing quantitative distributions for months and months now, through many units at this point. So this is a probability distribution. It's just like a regular quantitative distribution, except now our frequencies are not frequencies, they're probabilities. How often does each one occur? All right, so that's what we're going to be working with. Variables that represent chance process, outcomes from chance process. So let's get in and talk about discrete and continuous random variables. All right, let's get some vocabulary. Random variable, kind of mentioned this a couple of times now. Random variable. Variable means it represents multiple values. Random means it comes from a random processor, chance process. So, random variable is a variable that represents the outcomes of a chance process. So chance process, that's the random part. And we know that the outcomes of a chance process are known as the sample space. So for example, X on the last one, X was a random variable. X represented the possible sums from two four-sided dice. So random process or chance process and the possible outcome. So that's what that X represented. All right, now we have two different kinds of discrete random variables and continuous random variables. Big thing on random variable, if we're talking discrete and continuous, then random variables must be quantitative. Must be quantitative. So I wouldn't have things like heads and tails, something like that. We're going to be producing numbers because we want to be able to graph these things, or be able to calculate means and standard deviation, variance, things like that. So must be quantitative. Now we know that quantitative variables are things that come from counting or measuring, things that make sense to order on a number line. So that kind of gets into our first random variable we're going to talk about, which is the discrete random variable. Discrete just means that the numbers are countable. Countable. Okay. So when we talk about countable numbers, it's like things like 1, 2, 3, 4, 1.6, 1.7, 1.3. Okay. It's not getting into, and we'll talk in a second with continuous random variables. It means that there are discrete, there are definite possible outcomes. I know beforehand you're going to fit it, you're going to be this, or this. So if I was counting, say, the number of siblings that a random student has, those should be countable numbers, right? They should be somewhere between 1 and 100 realistically. And it could be more than 100 possible students, or siblings for a student, I don't know. But it's a number I could definitely count to. There's not infinitely many possible outcomes to that answer. So countable numbers, so a finite number of outcomes. So a finite sample space. That's what we mean by countable. So those are discrete random variables. Because it's finite, it's possible to list all values in the sample space. Possible to list all values in the sample space. All right. So with quantitative data, we like to describe with summary statistics like means, variance, and standard deviation. So what do we mean by the mean of a discrete random variable? Mean, you'll also heard referred to as expected value. So whenever somebody mentions expected value, they're just talking about the average of the distribution. Well, we don't have a true distribution where we list all the possible outcomes. We have a distribution a traditional distribution where we list all possible outcomes. We have a distribution where we list the probability of an outcome, or the relative frequency of an outcome. So if we're going to calculate the mean in this case, we're really doing what's called a weighted average. So we don't treat all values equally, we take into account how often each one is supposed to occur, the relative frequency of each one. So let's go through and let's calculate what we just had. Calculate the mean of that distribution of it. So if we were doing it like a true weighted average and we adjusted each one, I could take my 1, right? I just add them all up. All right, so 2 occurred once. I had 3s, I had some 4s, 5s, 6s, 7s, and an 8. And there were 16 possible outcomes. So all that stuff together gives you an average of 5, or an expected value of 5. That's just how we calculate mean. Let's see if we can kind of abbreviate this process a little bit, because there's a lot of repetition in here. So if I separate it out, I've got 2/16, right? 2/16. I've got 3/16 twice, correct? So I've got 3/16 twice. I've got 4/16 3 times. I've got 5/16 4 times. I've got 6/16 3 times. And 7/16 twice. And then 8/16 only once. 2/16. All right, we know all that stuff equals 5. All right, so what if I kind of clean it up a little bit more? Well, what do we notice here? We know through a little bit of fraction arithmetic, 2 times 1 over 16 is the same thing as 2 times 1 over 16. And 3 times 2 over 16. And 4 times 3 over 16. 5, 4/16, 6, 3/16, and 7, 2/16, and then 8, 1/16. Okay. Well, what do we see here? We see each of the values of the random variable, each value of the sample space, and what do they multiply by? Their respective probabilities. Well, that's what we're looking at right here. So that's what this formula for weighted average, or for expected value, or mean of the discrete random variable says. It says take each value of the sample space, multiply it by its respective probability, and just add them all up. So you're just multiplying the value times its probability, and add all of those products together. Value times its probability, all of them added together. So that's what we're talking about with the mean of it. So each value of sample space times its probability all added up. That's what sum means. Now, what does this expected value actually mean for us? And what do we mean by the mean of the discrete random variable? So the mean is just the average. So if we're going to interpret, because we're often asked to interpret what that means. All right, so that tells us that if we made many rolls many rolls of these two dice, if we made many rolls of these two dice, then the sum would be about 5 on average. So we could get this number also by taking our 2 dice, roll them, record the sum, roll them, record the sum, roll them, record the sum. I got hundreds and hundreds of times, and then that average should come out to be pretty close to 5. And so that's what we're looking for, expected value. What do we get? What's the long run sum, the long run average sum? Now that's one way we do it. We could do it by hand that way, or we could do, with calculator. But we also have our calculator that runs our statistics calculations for us. So the other way I could do this is I could go stat edit, just like we always do when we're keying our data in. So stat edit, and in L1, I'm going to put the sample space. And then L2, I'm going to put the probabilities. Sample space in L1, probabilities in L2. Now, if I want to get my mean, we know we get means from one of our stats. So I'm going to stat calc, grab one of our stats. Now we know that our list is L1. There's nothing different from what we've been doing all course long. What we haven't used yet is that frequency list. So for frequency list, that's where I'm going to put those probabilities. I'm going to put L2. So that's going to tell me, go to run a calculation, run one of our stats on list 1, but count each value in list 1 by its relative frequency. And then once we do that, it's just a matter of reading X bar. So we could go get X bar, and we know we do that. Like I said, you can go try that out, but if you'll key that stuff in, X bar, it'll come out and equal 0.5, or sorry, it'll equal 5. Right, so if we can get means, then we can get distances from means. Right, so next, let's talk variance and standard deviation. So what do we mean by variance? Well, variance is the same variance we talked about when we did learned about quantitative data and summary statistics many lessons ago, many units ago. Variance is nothing more than the typical squared deviation. Typical squared deviation from the mean, or from the expected value. So squared deviation, deviation means how far from the mean. Then we would square that, and then we're going to adjust for our relative frequency. So the by hand formula, take each value minus the expected value, square it, and multiply it by its respective probability. Just like we did when we did our variances way back when. Same thing here. Take the next value minus the expected value times its square it times its probability. Add all those up, and you'll get the variance of the distribution. Standard deviation is the same thing, except it's the square root of it. It's the square root of that sum of squared deviation. Now, we have a different definition for standard deviation. It's our typical distance from the mean. So it's the typical distance, typical just meaning average, typical distance of an outcome from the expected value. So on average, how far off is any particular outcome from that estimated 5 that we're supposed to get? That's our standard deviation mean. Now we could go through and do the form. I'm not doing this by hand. This is a pain. This is annoying. It's just a test because we've actually already done the work. We did the work when we did it up here, and we ran one of our stats with our calculator, because we know that one of our stats is going to produce not just the mean. It's going to produce interquartile, or sorry, it's going to produce quartiles, medians, sum of this value squared. It can produce lots of stuff, including sigma x. And yes, we would use sigma in this case because we have the entire population of that outcome. So not only can we get x bar off of that, we can get sigma x off of it. And sigma x, when we go to our calculator, so if you'll go back to where you just tried this out and saw that it equaled 5, if you'll go back and look again, you'll see that sigma x equals 1.58. Equals 1.58. So then to get variance, we just square it. So it's 1.58 squared, which is approximately 2.5. Now, we don't care so much, this number is important for future calculations, but we don't care as far as interpreting what that means. The interpretation that's important to us is this 1.58. So what is that 1.58 tons? It's the typical distance of a single roll from the expected value. So it says if we made many rolls of these two dice, we made many rolls of these two dice, the sum of the rolls or I guess the sum of the dice would typically differ from the expected value by 1.58 on average. So if I rolled the dice, recorded the sum, subtracted it from 5, rolled the dice, recorded the sum, subtracted it from 5, rolled the dice, recorded the sum, subtracted it from 5. If I did that again, hundreds of times, and I took all of those distances, so like the absolute value of the differences, if I took all of those distances, it would be pretty close to 1.58. That's how far on average a single roll is from actually producing a 5. We know 5 is the most possible outcome, most probable outcome. We know it's the expected value, but you're not going to get that every time. And what this says is typically you're going to be about 1.5 points or whatever you're measuring your sum in. 1.5 points off of that 5, so above or below on average. All right, last thing we'll talk is continuous random variables. How is it different from discrete random variables where it's countable and finite and possible to list the entire sample space? Continuous random variable is exactly what it sounds like. Random variable means it's representing the outcomes of a chance process, okay? Represents the outcomes of a chance process, but it's continuous. Continuous meaning that from one outcome to the next outcome, there are no gaps. So from 1 to 2, or 2 to 3, like we're talking about with our dice, from 2 to 3, there's a huge gap. There's an infinitely large gap between them because it's not possible to get a 2.1 for a sum, or a 2.0001, or a 2.9986325. There's infinitely many numbers between 2 and 3 that we couldn't possibly get as our outcome. So that's why those are discrete, because there are certain numbers we leave out. That's why it's finite. Now, a continuous random variable is not finite, it's infinite, okay? So the sample space has infinitely many possible outcomes. So it's something that if I'm writing out the sample space, I'm probably going to write it not in set notation, like these are the values, but I may write an interval notation. It's all values between 4.2 and 4.9, something like that. So continuous random variable, sample space has infinitely many possible outcomes. Well, what are some sample spaces? What are some random events that could have infinitely many possible outcomes. What if I was spinning a penny? So spinning a penny and timing how long that random penny spins for, there's infinitely many possible outcomes. So one penny would spin for a certain amount of time, and then the next penny is very unlikely to spin for the exact same amount of time, but it could. But it could be 100th of a second off, or a millionth of a second off, or a billionth of a second off. It may not produce the exact same outcome like rolling 2 dice do and adding those 2 numbers together. Those are going to produce a finite number of outcomes. Timing things, measuring things, produce infinitely many possible outcomes because those differences in measurement can be so tiny. So we want to think continuous random variable. That's typical of measurements. So these random variables kind of cover the 2 different ideas behind quantitative. What makes something quantitative? It's something that we've counted or something that we've measured. Counting things is discrete. Measuring things typically is going to be our continuous. Now, if we're measuring and rounding to a certain decimal value, then it becomes finite at that point. There's only so many values within that decimal place value. So, but when we talk about just measuring it truly, then it's continuous. So because we can't list all possible outcomes, we don't use a histogram like we did with our discrete random variable. We would use a density curve. So the graph of is a density curve instead of a histogram. So density curve is what we would use for continuous. A histogram is what we would use for discrete. Now, because I can't list all possible outcomes, I can't type my stuff into this nice little neat formula, or I can't type it into one of our stats on the calculator. So because we have this issue with being able to get all possible outcomes, the mean and standard deviation in this case, they're going to be calculated through calculus. And we're not doing calculus. This isn't calculus-based statistics. That's another course that you'll take later on in the future. So we're just going to have to be given the mean and standard deviation because we can't do the calculus yet. We're not calculating the area under the curve or calculating certain locations where we've balanced that area under the curve. So we're calculating inflection points and stuff like that. So calculus is how you get the means and standard deviation. So for most continuous random variables, you're going to be given, okay? So you're going to be given the mean and standard deviation. Well, that's not too different for us from what we've done before because we've done this when we did normal distributions. So think normal distributions when we're talking about giving you the mean and standard deviation. So I might have a measurement of something that we've calculated or a chance process that we've got going on, and I'm going to say this is the expected value, this is the standard deviation of it, and then we're going to get in and do whatever calculations or conclusions we need to draw from it. So we're going to use them the same way, we're just going to be calculating them differently. In discrete, you guys can calculate expected value and standard deviation. With continuous, you're going to have to be given the mean and the standard deviation, the expected value and standard deviation. Then we can go in and do our further analysis, the same way after that. All right, so that's it for random variables, and we need to understand the difference between discrete and continuous, and then how to calculate those expected values. That's the big idea for that. All right, so that's it for random variables, and I will see you in class tomorrow, guys.